We discussed a result, a theorem, in the last module, which gives us the necessary and sufficient condition when we can have a mixed strategy equivalent of a behavioral strategy. And that theorem was this one. So it says that the behavioral strategy has an equivalent mixed strategy if and only if each information set for that player intersects with every path starting from the root at most once. So you cannot have situations like where the same information set is intersecting with the same path multiple times, as we have seen in that example which represented some amount of forgetfulness. Now in this module we are going to discuss the opposite, that when can we have a behavioral strategy equivalent of a mixed strategy, and we will finally see that will give a sufficient condition for that, and that sufficient condition will also subsume the condition that we have given in this previous theorem. So therefore we can have an equivalence between mixed strategy and behavioral strategy. So with those conditions that we are going to state, you can have a behavioral strategy equivalent of mixed strategy as well as mixed strategy equivalence of a behavioral strategy. So these two things will be one and the same. So in order to define that, we'll have to somehow capture what is forgetfulness of a player. So we have seen a couple of examples for forgetfulness of the player, one in which the player forgets whether it has played at all or not, and the other condition was where the other situation was where the player has forgotten which action it has played. So we'll address both of this forgetfulness one by one. But before that, we need to define something. We need to define what is a choice of same action at an information set. As you can imagine, the name itself is quite explicit in saying what it means. So it is saying that if you have two different vertices, so let's say I have two different paths inside a network. So let's say one path is coming like this from root to here, and another path is possibly coming from the same root to some other node. Now what it is saying is that if you intersect any information set, so let's say you have two different nodes, let's say xk and xl, right? So these are the 2 points at which this path, these two different paths, let's say this path is x and this path is x hat, they're intersecting with this information set of player I. Let's say this is player i's jth information set. Then we say that these two different paths choose the same action at this information set iij, if of course k is less than the length of the path, and also l is l is less than the length of that path, and the action that you are picking. So for instance, if you are at this node which is inside this information set, and you are taking this action to go towards the end of this path, so going towards the next node in this path, then they should be the same. So if you are taking the same action, because in the same information set you have the same set of actions available to you, if this path, so let's say here you are taking a1, then it must be the case that here also you are taking a1 to go to the next level, the next node in that path. Then we are going to say that these two paths are choosing the same action at an information set of iij. This is just formally stating what it means, but the name itself, choice of the same action at an information set, is already saying what it is doing. Now I just want to make a remark that even though in this particular case we are just looking at the path which is from xk to xk plus 1, which means that it is the very next node in the same path, but it does not always, so this direction and the corresponding statement that xk leading to xk plus 1 does not always necessarily mean that it is just the next node in the same path. So I can have, let's say I have a bunch of nodes in a specific path, and I am just talking about, let's say this one is x and this one is y, and there are some intermediate nodes in between. So I can say that this action is leading to, so let's say this is the action A prime, which is leading to Y. So I can say that the action for player I, which starts, so which takes this path from X towards Y, this will be equal to A prime. So that is the meaning of this statement, that I can have a path which is leading to Y from X, but that Y need not be the immediate next node. So we'll be using this term leading to sometime later in this module. So therefore, it's worth noting what it means. All right. So now we have let us go to that particular condition where we can have this equivalence, or at least we can say that you can have a behavioral strategy equivalent of a mixed strategy, and that condition is what is known as perfect recall. Again, the name itself somewhat resembling what it means. Essentially, the definition rules out all those two cases that we have discussed in the example before, where the player was forgetting which action it has played, and it was forgetting whether it has played at all or not. So let's look at the first condition. So we'll say that player I has perfect recall if these two conditions hold. The first one is that every information set of player I intersects every path from the root to a leaf at most once. So this is actually ruling out the second kind of forgetfulness, where you had, so remember we had an example where these two nodes which were actually connecting a path from root to the leaf, and they were connected with an information set. So this condition 1 is actually ruling out that kind of a situation, because this information set is intersecting with the same path multiple times, and that is not possible according to 1. And the second condition says that every two paths that end in the same information set of player I, so again you can draw the picture that you have two different paths that end in the same information set for player I. So let's say player I has a specific information set IIJ, and you are looking at these two nodes which are coming via different paths, and they should, so every two such paths that end in the same information set of player I pass through the same information sets of I. So it should not be the case that they pass through different information sets in the same order. So you cannot have arbitrary order, so you will be sequentially going through all the information sets. So if there are other information sets, let's say J prime and more information sets of that player, then all these things, all these two paths will actually be intersecting through all of them in the same sequence. And then and in every such information set, the two paths choose the same action. So this is the most important thing. So if we because in the same information set, the set of actions are available to this player I is the same, they should also choose the same action. So this is actually ruling out that particular example where the same player were playing both left and right, and then it was in a situation where it had an information set there. So it means that it is taking, so here there was an information set, so here also player 1 was playing, here also player 1 was playing. So here player 1 was taking two different actions, and these two paths were actually leading to the information set where this agent of the same information set of that player. So this is ruled out by this second condition, because now we are ensuring that it not only takes the same sequence of information sets of the same player, it also takes the same action. So this cannot happen, that it is taking different actions and leading to the same information set. Okay, so this is essentially the definition, very carefully ruling out this kind of forgetfulness situations. So one can write this a little more formally. This will require a little bit of time to understand this notation. So let us go over it very slowly. So for every IIJ, so this is an information set of player I, and every pair of vertices in that information set, let's say x and x prime, so something similar to this one. We'll just go back to the same diagram back and forth. So if the decision vertices of I, so note that these are decision vertices of I, so those are the places where player I is essentially the player. So this sequence of nodes are only those places where player I is playing. So therefore these are only those places where you have the information sets of player I. There could be some intermediate nodes. So these are not sequential nodes in the path, because there are some more nodes where some other players are playing, but we are just picking out only those points where player I is playing. So let's create the sequence of those nodes where player I is playing with xi1, xi2, and finally the lth node is the node of x that we are comparing with. So this is x and this is x prime. So you have two different paths where these players are actually playing. So the same player I is playing, and this has a if you list them down, there are L such points, capital L such points in this path which is leading to x. There are k such so L prime such nodes which is leading to this other node x prime. Then three conditions should get satisfied. The first condition is this number L and L prime should be the same. So this is the first condition here. So you cannot have dissimilar number of points where player I is playing and you are leading to the same information set for that player. That is not possible. The second condition that should hold is that if you look at any intermediate point in this sequence of nodes, so let's say look at L and the corresponding L here, then they should belong to the same information set for player I. So we are going sequentially one by one and listing only those points where player I is playing, and we have ended up in an information set, in the same information set for player I. Then if you look back any previous node, so if you are looking at the same numbered node in both these two sequences, they better belong to the same information set for that player. And the last condition is the action leading from L to L plus 1. So here you can see that L and L plus 1, they need not be a parent and child relation. So there might be some intermediate nodes in between. But because this is a game tree, so this path which is leading from xi to xil to xil plus 1 will be unique, and the action that is taken by this player at that point for both these nodes, so xil to xil plus 1 and xi prime l to xi prime l plus 1, these two actions should be the same. So this is essentially capturing those two conditions that I have said in words here. So that is being formally written with the notation that we have used so far. So we'll also call a game to be of perfect recall, the entire game to be having perfect recall, naturally if every player has a perfect recall. So this definition, as we have already mentioned, the first condition essentially is subsuming the condition of that theorem, of the previous theorem that we shown before. So therefore, I mean, that condition was necessary and sufficient for every behavioral strategy to have a mixed strategy, equivalent mixed strategy. Now we will show that with this perfect recall definition, which is a more strict definition than that, because we already have that condition, as well as we have the second condition, which is also added on top of that. So it is a more restrictive definition than the previous one. We'll see that we have equivalence in both directions. So let us look at some examples to understand what this game with perfect recall mean. So this example, if you look at, so there are three players. Player 3 is playing first, and based on its two actions, either one can play or two can play. Then based on their actions, you can come back to one again, and based on player 1's action, there could be this kind of situation. So why is this example of a this example is that of a game with a perfect recall? Because if you look at those two statements that you have, so let us look at the text statement. So every information set for that player intersects with every path from the root at most once. So there is no such a situation where the same information set is intersecting with the same path from the root multiple places. And the second condition was that there were two paths that end in the same information set. They will pass through the same information sets of that same player in the same order, and in every such information set these two paths choose the same action. So of course this second part we cannot verify because there is only one situation. So there is no previous information set of either 1 or 2, but at least we can see that the first condition is getting satisfied, and also the second condition is sort of vacuously satisfied. But if we look at modify the game slightly by introducing this player. So instead of player 3, now player 1 is actually making the first move. Then this is certainly violating the condition that it is not taking the same action. So you see that it is taking two different actions. But if you look at this nodes, let's say this is x and x prime, and if you look at the path starting from the root to this node, in the previous information set of the same player, which is this, the player was taking two different actions. One is taking this action, the another was taking a different action to reach to these two different nodes. In some sense, as we have showed in the previous example as well, this player 1 is actually forgetting which action it has played. So that is why it is in this information set. It is forgetting what action it has picked in its previous round, and that is not allowed according to the definition of perfect recall. So let us also look at what are some implications of perfect recall. So the perfect recall definition will also give rise to certain equality in the strategy sets. So let's define this one. So let's say Si star of X be the set of pure strategies of player I at which he chooses the actions leading to X. So there might be multiple actions. So let's say we are at a specific node X at some node in this game tree, and there are maybe multiple information sets which are actually leading to this X. So maybe this path, and then there are other information sets of the same player. So let's say PI 1, II 2, and so on. So this is IIJ, for instance. And if you look at all these, if you collect together all the actions that has actually been taken by this player I to reach to this node X, that those collection of all those actions or the strategies will put as Si star of X. So these are the set of pure strategies of player I at which it chooses the action leading to X. That is the intersections of this of the members of Si with the path from root to X. So then we have this theorem. It says that if I is a player with perfect recall and X and X prime are two vertices in the same information set of I, so now X and X prime, let us assume that it is also a member of some information set for player I, then it must be the case that the corresponding sets that we have just defined for these two nodes X and X prime should also be the same. So this conclusion essentially is a result of that condition that it should come from the same sequence of information sets, and you will take the same actions at those information sets. So collecting all these points together, we can actually now state the theorem, which is essentially a sufficiency theorem due to Kuhn in 1957. So in every imperfect information extensive form game, if I is a player with a perfect recall, then for every mixed strategy of player I, there exists a behavioral strategy. So of course the converse is already true, because the game of perfect recall already considers the necessary and sufficient condition where behavioral strategy has a equivalent mixed strategy. That direction is if and only if, though here it is just a sufficient condition. So together we can say it is safe to have a game with a perfect recall where we can use behavioral strategy and the mixed strategy interchangeably. So I'm not going to prove this. This is straight from the book of Maschler, and this theorem 6.15 can be read in order to find the corresponding proof. The proof essentially, let me give you the intuition. It's a constructive proof. It starts with a mixed strategy and essentially constructs the behavioral strategy such that the probabilities of reaching a leaf, reaching every leaf node are the same. And this argument essentially uses the fact that we have defined the definitions of perfect recall, such kind of a construction is always possible because it's a game of a perfect recall.